Hello everyone and welcome, I'm Camille. Today's video has been requested by one of the supporters on the Coffee page. So some of you guys basically ask how to do constraints in Kinefx, and I will show you today how to do two different types of constraints. One of the constraints is basically constraints in your rig. For example, you want to constrain one joint to another, you want to constrain controls to the joints, and etc. etc. The other type of constraints which I will show you are on the object level. So for example, you want to constrain, let's say, the left arm to another object or something like this on another rig. So I'll show you how to do those two things. So let's jump, and first of all, let me show you how to do constraints inside of the rig by using a Kinefx nodes and allow editing contents. So I'll basically show you how to use the parent constraint node, the VOP node, and also I will show you how to recreate it by yourself so you have an understanding what's going under the hood. First of all, I have a frog rig, which you've seen it before, with a simple animation on the root. That's cool. Let's dive into rig, and let's just display for now all the things happen to a spine. So we have a spine rig here. That looks cool. This is our spine skeleton. It's moving, and let's say the constraints method, which I will show it to you, it works. You can have the joints in the same joint chain. You can have your extra joint which you want to parent in the same joint input or something like that, or you can have it as a separate one, and you can blend and add everything together. This workflow is super versatile and elastic to modify. So first of all, let me create a skeleton, new skeleton here, and let's say that will be skeleton. That could be like a hat rig or something like that. Yeah. So let's go to the maybe a right view or something like this. Let's enter the rig state, and I will go view. The view basis. It's enough, and I can just place two joints here. Cool. And let me just go to the quicker mode, move it here, for example. Why not? So, and let's go to the rig tree. Let's call the joints respectively. I will call it head fun GNT, and I will call this one head fun underscore end GNT. Doesn't matter, you can call it hat, whatever it is. It's just for that training purpose. Okay. Sorry, some mouse issues. Okay, let me close that window. So this is our skeleton which you just created. Let me just exit rig the state, Python state. Oh, it's actually, you can see that the joint is a little bit placed not exactly in the middle. I can easily edit that. We can go to the rig tree. We can select the joints. We can enter the Python state. Enter the joints. Press the P key, and we can just in the X can just modify these two guys so that will be exactly as we want them. For example, in the middle, doesn't matter. And we can exit the Python state. Fantastic. So we have a joint in the middle, and we basically want to parent that joint chain we just created to follow the head GNT. And if you look at it, if you open the rig tree, you can see that the head is here. It's a head GNT. And if you don't know which joint it is, if we enter the Python state by pressing the enter key, you can see it's here. It's a head GNT. So we want our joint to actually follow that one. So how to do it? First, we'll do it with the fastest way. We'll create the rig-VOP node, and we'll just, as a first input, we'll bring our skeleton. As a second input, we'll bring our spine. So basically the input where there's drivers, right? We enter the rig-VOP node. Just make a little bit of a space, hopefully you can see. And let's get the transforms. First, we need to get the matrix for our our new skeleton, the head fun, right? And it's super easy to do. We can just do it by name. We'll type the name here, head fun GNT. Fantastic. And I can just call it head fun. That looks good. Let me just copy, paste, and duplicate this one. And this one will be bringing transform from the second input, and will bring the head GNT. Cool. Let's just rename it head GNT. Cool, why not? And that looks pretty cool. So we have a parent, basically matrix here, which are coming from the X1, which is war matrix, and we have our head fun, and we have a war matrix as well. Now, the easiest way to do it is to use a parent constraint. Not to do it. So, as a first input, you want to apply the matrix of an object, of a child basically, of the object which you want to drive. So we want to drive our head fun. Okay, let's plug it to the X1. And now, lots of people do the mistake and they apply the parent matrix to the parent. It's not what you want to do. You want to bring it as a new parent. When you select the parent constraint, you can update the offset. It's necessary because we need to calculate the offset by from the bind matrix to that one which will be moving, and I'll explain it to you later what's happening under the hood. And let's export that transformation back to the head file. So we'll do the set point transform. Cool. And we'll output the transform to the first input. Sorry, to the first input, yes, but to the point number of that chain. Yes, perfect. So now if you go up, if we display our rig VOP, we can exit the bind to stay. We're just gonna see here our head fun join. If you want to see both of them, you know, the skeleton and everything, we can use the merge node. Let's do it. That's just for, you know, visualizing it. Why not? We can merge those two skeletons just for visualizing. Okay. But now, if you scrub the timeline, you can see our head fun is basically following the head join. Wow, that's pretty cool. And that's it. That's how you do your parent constraints. Now you have obviously the blend. You can just, you know, smoothly blend it, and you can do all other stuff. You can choose which channels you would like to have constraints and etc. So you can have a one parent constraint for, you know, translation, other constraints for rotation, etc. Okay, that's pretty cool. But you know, it's very simple matrix operation. You can dive in that node and see what's going on. But also, let me explain it to you how to recreate this kind of behavior by yourself. For you guys who knows matrix operations, etc. Again, guys, skip the video a little bit further. But for you guys who doesn't know, let me just show you what we need to do. Okay, sorry for my drawings, but here I'll try to explain what we try to do. The gray arrows represent the origin of a scene. Basically, good to remember that everything in Kinefx is a word space matrices. Even that point here, which I drew as a P, it is actually under the hood, is a word matrix, which is fantastic because we not only have a position, but we also have an orientation. Okay, so what we want to do, we basically want to take our point P and want to parent it under the red matrix in such a way that if we rotate the matrix, right, the red matrix, the point P will be transferred accordingly and will be moved, you know, to the right place. Cool. And we obviously like to transform our, you know, red matrix by the M matrix or whatever you call it. So what to do to put our point P? We need to basically do all of that calculations of moving that point P here. We need to do by ourselves. It's actually very simple. It's simpler than you think. If you look at all of those arrows, the matrices sometimes I refer as a, you know, coordinates frame and etc. That looks like a coordinate system. That looks like a coordinate system. That looks like a coordinate system. If you don't know basic matrix operations, you can always watch some videos on Khan Academy or something like that. It's always good to, if you work in 3D, to know those basic stuff. But let's get back to what we need to do. First of all, we need to get the inverse matrix of the red matrix in order to bring everything down to the origin. So we basically need that matrix by reverse inverse matrix. So let's say we calculate that matrix, and that matrix will let us to bring things to the origin. And now if that by that inverse matrix we multiply our point P, and we're getting P prime, that's cool. And from this point on, all what you need to do is by this matrix here, or this matrix, like, you know, where is the control in the current frame, all what you need to do is to multiply the point P prime by this matrix. That's it. That's it, what it is. You don't need to, you know, do any other transformations. That's it, what all you need to do. So it's very simple and it's super fast. It's a very good way to, like, you know, bring your things together in your rig. So when we multiply a P prime by this matrix here, you'll get the final PF. Cool. There's one gotcha here, but you need to remember. We need to store this matrix here in the memory in a way that we can always refer to it. What does it mean? You know, the parent will be always moving through the time, right? So we somehow need to store the moment where we say, at this time, I want to parent, you know, this P to this matrix. So we need to store this initial binding matrix. That's very often what you see on some, you know, constraints nodes and something like that. There's sometimes an update button or something like this that lets you to update this binding matrix, because you need to have some information about how to, because you somehow need to calculate this, you know, different, you know, the difference between the transformations. You need to have that. Actually, we need that matrix to actually have a right inverse matrix. That's it. Sorry, I don't want to confuse you. We need to store that matrix to have the right inverse matrix. And I will show you how to do that. It's super easy. And when we do it in the nodes, you'll actually get it straight away. So let me create a new rig VOP node. VOP. Okay, we do the connection the same way. And I will dive into the old one and I will copy those two nodes, so the set point transforms and the get point transforms. Okay, so we don't need to recreate them. Cool, let's bring them in here. Let's break the connection, why not? Cool. Let's go up one queen and let's just display the output of the rig VOP so we can see what's happening. I will show you some difference. So the currently what is displaying, you know, the input of the first input, so it's a head fan in that case. So as you remember, the first thing what we need to do is to store the binding matrix of the head joint. How to do it? Super simple. We have an amazing node here, stash transform, which is really cool. And as the first input, it takes the, you know, the information where the data come from, the point index, and the matrix. Yeah. And now you can see here the matrix which is stored. In order to store it, you just press the stash. And that stores the transformation, the world transformation of the head joint, not the head fan, the head joint, our parent. Cool. And now, if you scrub the timeline, that matrix doesn't change, but the head joints will change. I can visualize it for you. For example, I can plug the matrix of our head as, so this is where our head is, you know, and our head is moving, yes, but our stash matrix isn't moving. You can see that. Cool, that's a difference. But let's do not confuse you guys here. Let's break those connections. Let's get back where we are. And let's just connect this one back here. And here you go. So now what we need to do, as remember from our drawing, we need to invert that matrix. Super easy. We just have an invert node for that. Cool. You remember, we need to bring the head fan to the, we need to multiply the head fan by the inverse matrix, which we just calculated. Super easy. We can use multiply node and just multiply it by that inverse matrix. Cool. And now we can display it. You probably will know what's going to happen. You're going to see the head fan just moved slightly here. Yes, closer to the origin. Cool. And as you remember at this stage, all what we need to do we need to multiply by this matrix that we just got here, but the head joint matrix which is moving. Okay, so we can do it super easily. We just type multiply, here we go, and we can just apply our x from here. So for you guys, so you can see better, as a first input is our head fan multiplied by the inverse matrix. As a second input, our head joint, basically the matrix of a parent, right? And we're plugging it back, and voila, our head fan is where it should be. Cool. Let's go up, and let's just scrub the timeline. Yep, everything is moving. In order to visualize it better, let's bring the merge node. Let's merge those two outputs together so we can see them together. And if you click the visibility flag, yep, you can see that our head fan is here. So basically, that method of like multiplying matrices is really fast, and it's really good to use that method instead of using a joint parent, reparent joints or something like that, because the reparent joints, it's using unfortunately a Python inside, and it's have a different purpose. It's not for fast rigging here. It's something much for more operations which are not really a time dependent, and performance is not your consideration. Cool. So if you want to do any reparenting and parent constraining, this is the right ways to do it. Also, you can use the VEX code. You can watch the video about the space switching where I did everything with the VEX, and you can basically take the VEX operations and write it in a VEX, which is gonna be much cleaner if you want, but it's up to you how you approach that. So this is the way how you do a constraint inside of your rig. Cool. Okay, now let me just match the current definition so it removes all the things which we just did a second ago. What about the constraints in object level? So as you can see here, our HDA is a locked HDA, right? We can't really go here, we can select those controls. And also, as you remember, those controls have been created by a special script which creates this cool setup of rig 0 and connects everything to the rig pose, and all of those object level controls are created automatically. That creates a little bit of a problem, that if you want to use on-shelf tools for constraining, that doesn't really work well with this one we have created here. So we need to modify it a little bit, but it's super easy, and I will do it step by step so you can create those constraints by yourself. Okay, let's create an object. In that case, maybe a null. Why not? That will be simple enough. And that null will be a parent for our, let's say, a head of k, right? I'll move it somewhere here. Doesn't really matter. Let's change the look of it a little bit. Make it a little bit smaller. Let's just make it flatter. And let's just change the... maybe a circles. Yeah, that looks pretty cool. I'll change the color for the red one. It looks cool. Yeah, that's fantastic. So that will be our parent for our head FK control, and we will do it with a chops. So what we want to do, we basically want to drive parameters here with a chop network. Okay, super easy to do. First of all, let's create a chop network. And let's get the matrix of the parent of this head FK control. So because we know those controls are in a hierarchy, and we want to get the parent matrix here because we don't want any cycle dependency. So in order to get that, we have a handy node called get parent space. And here you can choose the node. You can choose it in the viewport, or you can choose it here. Export relative path, why not? The one cool trick when you're working with chops is that if you press T key, so you're in your translation, and you select any of your motion effects nodes, basically the chops nodes, you can see the frame, basically the matrix here. It's super cool for debugging. You will see in a minute. Now let's bring the matrix for our parent control, that red circle. We use it object constraints node here. Let's choose our parent in that case. That will be an null. And now remember, if you select it, we can see the matrix here. So I have one matrix here, one matrix here. Now, as you remember, we need to remember the pose, the binding pose for creating constraint. And at Chops we have a great node called pose. But with the version of Houdini which I'm using right now, there's a slightly issue here with it. There's an error. Let me show you. It doesn't mean that you're gonna encounter this error. The error encounters, I think, with the Houdini which is using a Python 3, and I will show you how to fix it. So basically, when you click the update pose, you're getting the error that the reload is not defined. Looks like that somebody left the reload function there while I was working on that node, and after switching to Python 3, that wasn't removed. The easiest way to fix bugs like this, if you would like to, it's to create a copy of this node, edit it, and save it as your one. So what we're gonna do now is basically we're gonna show the asset manager. We're gonna duplicate it. We'll call it my pose, why not? And I will save it with my hips. Accept it. Cool. So now if I tap my pose, sure, here, I can remove this one. Yeah, it's my pose. And so basically to fix it, you right click, go to the type properties on your node, would you just bring it in. When you go to the update button, you can see that here is the reload called at some point. Looks like somebody was working on it. Just left it there when I was testing the node. The easiest way to fix it is, for example, to type from import lib import reload. Click apply, accept, and now press update button. You can see we store the matrix. No matter what we change the values, the matrix is stored here. So that was the binding matrix. And now you can see when I click here, I can still, see that matrix, yeah? So we have gonna have one matrix which will be moving over the time, and we have a one which is always stored where it was. Kind of like a reference pose or binding matrix. Okay, that's pretty cool. Now, what we need to do, we need to calculate the difference between the matrix which is moving and the matrix which is stored. We can do it very easily with pose difference. Super cool node. Just plugging those two, and we're getting the difference matrix between those two. That's cool. Now, all what you need to do is to use a simple blend. And this is the node which you want to blend. And this is our blend. And we can actually bring everything back with the new animation here. Now, we cannot export that yet. The reason why, because our channels are called TX, TY, TZ, TRX, and etc. As you remember, we want to drive our channels on our HDA, and the channels here are called the head FK control underscore TX and the head FK CTRL underscore TY, etc. So we need to add the prefix to that channels in order to export it. Super easy. You can do it with rename node. So let me copy the name, which I'm gonna add in as a prefix, create the rename node. Okay, turn it on, why not? I'm gonna rename all the channels to this head FK control with asterisk. So now, middle click, that's the name of the channels. As yes, you guessed right, we need to specify where we'll be exporting it. I'll be exporting to the main HDA, right? Cool. In order to make it work, we just need to click the export, and that's it. That's your constraint. In order to prove that it's working, we can just select our null, and we can just move it, rotate it, translate it, whatever we want. Cool. Now, you can just take all of that and wrap it as a simple, network, and just have one input or some attributes to create those constraints super easily with a simple button to update the matrix. I think I will add such a thing like that to our Kinefx tools. Why not? Let me know, guys, in the comments if you would like to see it. Thank you for watching the video, and thank you so much for your support on the coffee. For you guys, if you don't know what the Kinefx tool is, it's a free GitHub repository where you can find lots of useful HDAs, scripts, some tutorials about rigging in Houdini, mainly with using a Kinefx, which is a new way of rigging in Houdini. If you're finding what I'm doing useful and you would like to support me, go on my support me page and you can always buy me a coffee, and all the supports is very appreciated. And thank you so much, guys, for supporting. And you can reach me on Twitter, GitHub, anywhere you'll find me. Send me a message. I'm always happy to help. And yeah, thank you so much, and see you on the next video, guys. Thank you.